November 24th, 1943, 0300 hours, North Atlantic, 200 miles east of Newfoundland. The SS John P. Gaines rode through moderate seas under a moonless sky, her holds packed with 10,000 tons of military cargo bound for Liverpool. 44 merchant seamen and 20 naval armed guards slept in their bunks or stood watch on a vessel that had been launched just 8 months earlier from one of Henry Kaiser's Richmond shipyards in California. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. The temperature hovered at 28 degrees Fahrenheit. Ice formed on the deck railings. The water temperature measured 34 degrees. In the engine room, the triple expansion steam engine maintained its rhythmic pulse, driving the 441-foot vessel through the Atlantic at 11 knots. Everything seemed routine. The Gaines was just another Liberty ship in just another convoy, carrying just another load of war materials to sustain the Allied offensive against Nazi Germany. Then, without warning, without any preliminary sound or vibration to alert the crew, the entire ship split in half. The fracture began at the square corner of No. 3 cargo hatch, precisely where a welded seam joined 2 steel plates on the main deck. The crack propagated at nearly the speed of sound through the cold, brittle steel, racing along welded joints that offered no resistance to its progress. In less than 3 seconds, the crack had travelled the full length of the vessel, severing the ship into 2 separate pieces. The bow section tilted forward and began to sink. The stern rose at an impossible angle, the propeller still turning uselessly in the air. 10 men died in those first moments, trapped below decks with no chance of escape as freezing Atlantic water rushed through the broken hull. The 34 survivors abandoned ship in lifeboats and rafts, watching in horror as both halves of their vessel disappeared beneath the waves within 15 minutes. They were rescued hours later by convoy escorts, suffering from hypothermia and shock, unable to comprehend what had just happened. Ships don't simply break in half. Steel doesn't fail that catastrophically without warning. Yet the John P. Gaines had done exactly that. And she wasn't the first Liberty ship to suffer such a fate. She wouldn't be the last. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis facing the United States Maritime Commission in late 1943 represented one of the most urgent engineering mysteries of World War II. Liberty ships, the emergency cargo vessels that formed the backbone of Allied logistics, were failing in ways that defied conventional understanding. Some developed cracks that split their hulls open. Others suffered complete structural collapse while sitting peacefully at dock. A few broke entirely in half at sea, taking crews and cargo to the bottom of the Atlantic. Nearly 1,500 instances of significant brittle fractures were recorded during the war. 12 ships broke completely in half. 3 of those sank with loss of life. The question consuming naval architects, metallurgists, and military planners was brutally simple. What was killing the Liberty ships? And more urgently, could the problem be fixed before it crippled the entire Allied supply chain? To understand how American shipbuilding arrived at this crisis, one must return to the desperate circumstances of 1940 when Britain stood alone against Nazi Germany. German U-boats were systematically destroying Britain's merchant fleet, sinking vessels faster than British shipyards could replace them. In 1940 and 1941, U-boats and surface raiders sank 2,963 Allied ships. The mathematics were simple and terrifying. Britain would be starved into submission unless America could build replacement vessels at unprecedented speed and scale. The British government approached American shipbuilders with an urgent request for 60 emergency cargo ships based on a simple, outdated design from a 19th-century tramp steamer. The design was deliberately primitive, a coal-burning vessel with a reciprocating steam engine that would have seemed obsolete even in 1917. But it had one critical advantage: it could be built quickly using traditional shipbuilding methods. British naval architects had already modified the design slightly, creating what they called the Ocean Class. They needed American industrial capacity to turn that design into reality. The U.S. Maritime Commission, established in 1936 to revive American merchant shipbuilding, accepted the challenge. But the Commission's chairman, Admiral Emery Scott Land, recognized that traditional shipbuilding methods would never produce vessels in the quantities required. In peacetime, it took 6 to 12 months to build a cargo ship from keel to launch. Skilled workers built each vessel individually, riveting tens of thousands of steel plates together, using techniques that hadn't changed substantially in half a century. That approach simply wouldn't work for an emergency program that would eventually require thousands of ships. The Commission modified the British design to conform to American construction practices and, more importantly, to enable radically faster production methods. They designated the new vessel EC2SC1, Emergency Cargo, 400 to 450 feet long, steam-powered, Design C1. The modification that would prove most consequential was a seemingly simple change: replace riveting with welding as the primary method of joining steel plates. This decision was not made lightly. Riveting had been the standard method of ship construction for nearly a century. The technique was well understood, reliable, and proven. A riveted ship consisted of overlapping steel plates held together by thousands of rivets, each one heated red-hot, driven through aligned holes in the plates, and hammered to form a secure connection. The riveted joints created natural breaks in the steel structure. If a crack developed in one plate, it would stop at the rivet line and not propagate into adjacent plates. This redundancy made riveted ships remarkably resistant to catastrophic failure. But riveting was slow, labor-intensive, and required highly skilled workers. A single Liberty ship design required approximately 800,000 rivets. Each rivet had to be individually heated, positioned, and hammered by a team of workers. The process was noisy, physically demanding, and consumed enormous amounts of labor hours. In peacetime, with an adequate supply of experienced shipyard workers, riveting was acceptable. In wartime, with the need to train hundreds of thousands of new workers and build ships at unprecedented speed, riveting was impossible. Welding offered a revolutionary alternative. Instead of overlapping plates held together by mechanical fasteners, welding fused plates edge to edge, using intense heat to melt the steel itself, creating a continuous joint. A single Liberty ship required approximately 50 miles of welding seams instead of 800,000 individual rivets. Welding was faster than riveting. It required less skill to learn the basics. It was less physically demanding, and critically, it saved weight, as much as 300 tons per vessel, because plates didn't need to overlap. The technique had been used successfully in some applications. Germany had employed welding in constructing its pocket battleships in the 1930s to reduce weight while staying within treaty limitations. The Maritime Commission's own standard cargo ships, designed before the war, used welded construction. But no one had ever attempted to mass-produce welded ships on the scale the Liberty ship program required, and no one fully understood the risks inherent in creating vessels where the entire hull was a continuous welded structure with no natural crack arresters. Enter Henry John Kaiser, the industrialist who would transform Liberty ship production from a theoretical emergency program into the greatest demonstration of American industrial might in history. Kaiser was 58 years old in 1940 when he entered the shipbuilding business, and he had never built a ship in his life. His reputation had been forged in massive civil engineering projects: the Hoover Dam, the Bonneville Dam, the Grand Coulee Dam, the San Francisco-Oakland Bay Bridge. He had learned to organize enormous workforces, coordinate complex logistics, and deliver projects on impossible schedules. His approach emphasized speed, efficiency, and innovative thinking over traditional methods. He was, in short, exactly the kind of outsider the Maritime Commission needed to revolutionize an industry that had changed little in decades. Kaiser's entry into shipbuilding began with a partnership with Todd Shipyards to build ships for the British government. Todd provided the shipbuilding expertise. Kaiser provided the organizational genius and willingness to challenge conventional wisdom. The partnership established yards in Richmond, California, and other West Coast locations. But Kaiser quickly recognized that traditional shipbuilding practices, even with welding, would not achieve the production rates the war demanded. His breakthrough insight came from an unexpected source: the Ford Motor Company assembly plant in Richmond, located on the same docks where Kaiser was building his first shipyard. One of Kaiser's associates visited the Ford plant and observed how Henry Ford had revolutionized automobile manufacturing through assembly line production and the use of interchangeable prefabricated components. The visitor returned with a radical proposal: build ships the way Ford built cars. The idea seemed absurd. Ships were massive, complex structures weighing thousands of tons. They weren't consumer products that could be stamped out on an assembly line. Traditional shipbuilding had always been a craft, with hundreds of workers crowding around a single vessel on the ways, building it piece by piece from keel to superstructure. That was simply how ships were made. Kaiser rejected that assumption entirely. If Ford could prefabricate automobile subassemblies in separate facilities and bring them together for final assembly, why couldn't ships be built the same way? Instead of constructing every component on the shipway, why not fabricate entire sections of the hull, complete deckhouses, bow units, stern frames, and engine foundations in specialized shops, then move them to the shipway and weld them together? The approach required completely reimagining the shipbuilding process. Traditional shipyards were measured in acres. Kaiser's yards would cover miles to accommodate the flow of prefabricated components. Instead of skilled craftsmen building unique vessels, Kaiser would employ assembly line workers performing repetitive, specialized tasks that could be learned in days or weeks rather than years. Instead of building ships sequentially, Kaiser would build them in parallel, with multiple vessels at different stages of completion moving through the yard simultaneously. The workforce Kaiser assembled reflected the desperation and opportunity of wartime America. Skilled shipyard workers were in short supply, already committed to naval contracts at established yards. Kaiser recruited wherever he could find labor: farmers, factory workers, housewives, minorities who had been excluded from skilled trades in peacetime. Women comprised a significant portion of his workforce, performing welding and fitting tasks that required precision rather than physical strength. African Americans found employment in Kaiser's yards at rates unheard of in other industries. The famous image of Rosie the Riveter, symbolizing women's entry into wartime industrial work, was ironically misnamed for Kaiser's yards, where riveting had been almost entirely replaced by welding. Kaiser's publicity department tried to promote Wendy the Welder as an alternative, but the name never caught on. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. These workers, most of whom had never seen a ship under construction, were trained in a matter of weeks and put to work building the most complex industrial products of their era. The training was necessarily abbreviated. A complete novice could be trained to perform basic welding tasks in little more than a week. More complex operations required additional training. But Kaiser's system was designed to break shipbuilding into tasks, simple enough that newly trained workers could perform them reliably. The results were extraordinary. The first Liberty ship, the SS Patrick Henry, was launched on September 27, 1941, at the Bethlehem Fairfield Shipyard in Baltimore after 244 days of construction. President Franklin Roosevelt attended the launching ceremony, delivering remarks that gave the Liberty ships their name. He invoked the spirit of Patrick Henry, the Revolutionary War patriot who had declared, "Give me liberty or give me death," and proclaimed that these new vessels would be Liberty ships carrying the arsenal of democracy to Britain's defense. But 244 days was far too slow. By the time the Patrick Henry reached Britain, U-boats might have sunk dozens more merchant vessels. The war would not wait for traditional construction timelines. Kaiser's prefabrication and assembly line methods began to show results almost immediately. Construction time dropped rapidly as workers gained experience, and Kaiser refined his processes. By late 1942, the average construction time had fallen to 70 days. By 1943, the average was 42 days from keel laying to launch. The most efficient yards were completing ships in less than 3 weeks of actual construction time. The achievement was staggering. 18 shipyards across the United States were building Liberty ships simultaneously. At the program's peak in 1943, 3 Liberty ships were being launched every single day. The yards were delivering vessels faster than U-boats could sink them, reversing the deadly mathematics that had threatened to starve Britain into submission. Kaiser's competitive spirit drove production even faster. He encouraged rivalry between his different yards, offering rewards and recognition to crews that broke speed records. The Oregon Shipbuilding Company launched the Joseph N. Teal in just 10 days, in September 1942. President Roosevelt secretly attended the christening, performed by his daughter Anna Boettiger. The 10-day record made national headlines and seemed like the absolute limit of what was possible. Then Kaiser's Richmond Yard No. 2 shattered that record. On Sunday, November 8, 1942, workers laid the keel for the SS Robert E. Peary. The yard assembled the vessel using every time-saving technique Kaiser's engineers had developed. 17 banks of welding machines on each side of the hull, the deck pre-assembled in 7 sections instead of 23, deck houses completely outfitted with bunks, fans, and flooring before installation. 4 days, 15 hours, and 29 minutes later, on Thursday, November 12th, the Robert E. Peary slid down the ways into the water. The achievement was impossible by every conventional standard of shipbuilding. The Peary's construction time would never be matched, as the Maritime Commission eventually ordered an end to such stunt ships, recognizing that the extraordinary coordination required for these record attempts disrupted normal production. But the symbolic value was immense. America had demonstrated that it could build a 10,000-ton ocean-going vessel faster than most people could build a house. Behind these production miracles lay Kaiser's systematic application of mass production principles to shipbuilding. Components were standardized and interchangeable. Parts manufactured in one facility would fit ships being built in any of Kaiser's yards. Prefabrication moved much of the work away from the congested shipways into specialized shops where conditions were better controlled. Double bottom sections, stern frame assemblies, bow units, complete deck houses, all were fabricated separately and lifted into place by massive cranes. Welding was the technology that made this approach possible. Prefabricated sections could be joined quickly and efficiently. Welders could be trained rapidly. Machines could perform some welding operations automatically, even faster than human welders. The continuous welded structure created a lighter, more spacious hull than riveting allowed. By late 1943, the Liberty ship program was succeeding beyond anyone's initial expectations. 2,710 Liberty ships would eventually be built between 1941 and 1945, easily the largest number of ships ever produced to a single design. They were carrying the supplies that made Allied victory possible. Tanks, aircraft, ammunition, fuel, food, medical supplies, troops, everything needed to sustain military operations in Europe, Africa, and the Pacific. But even as Liberty ships streamed from American yards at unprecedented rates, carrying the arsenal of democracy across the world's oceans, some of those vessels were developing cracks, small fissures in welded seams, larger fractures in deck plates, structural failures that seemed to come from nowhere, and, in a few horrifying cases, complete catastrophic failure that split ships in half and sent them to the bottom with their crews. The problem first became apparent in the winter of 1942 to 1943, when several Liberty ships developed significant cracks while operating in the North Atlantic. The fractures appeared suddenly, without warning, often originating at square corners of cargo hatches where welded seams intersected. Some cracks extended for dozens of feet along the deck or hull. A few ships suffered such extensive cracking that they had to be abandoned or scuttled. Initial suspicion fell on the welding itself and on the workers performing it. The shipyards had trained thousands of welders in a matter of weeks, many of them women and minorities who had never worked in heavy industry before. Perhaps the training was inadequate. Perhaps the welders were making mistakes that created weak joints. Perhaps the frantic pace of production was causing workers to cut corners, producing inferior welds that failed under stress. The U.S. Coast Guard and the Maritime Commission launched investigations. Inspectors examined welds on dozens of ships, looking for defects. Some poor quality welds were indeed found, particularly in early production, when training programs were still being developed. Weld defects could certainly act as crack initiation sites, but even ships with high-quality welds were cracking. Something more fundamental was wrong. The fractures seemed to occur most frequently in winter, when ships were operating in the coldest conditions. They happened more often in the North Atlantic than in warmer waters. Ships sitting peacefully at dock sometimes developed cracks overnight when temperatures dropped. In one dramatic case, the T2 tanker Schenectady split completely in, half while moored at the dock in Portland, Oregon, in January 1943. The ship had just completed construction. It was sitting in calm water with no cargo, no stress, no apparent reason to fail. Yet the hull simply fractured from deck to keel, dividing the vessel into two pieces. The winter of 1943 to 1944 brought the Liberty ship crisis to its peak. The casualty rate for what the U.S. Ship Structures Committee would later classify as Class 1 failures fractures that endangered the ship or resulted in its loss reached 4.3 per 100 ship years. This was more than 4 times the pre-war loss rate from all causes combined. For comparison, U-boats, mines, and enemy action of all types were sinking Allied merchant vessels at a rate of approximately 1 per 100 ship years. The Liberty ships were, in effect, sinking themselves at 4 times the rate that enemy action was destroying them. The implications were staggering. The United States had committed billions of dollars and millions of labor hours to building an emergency fleet that was supposed to overwhelm German U-boats through sheer numbers. Now that fleet was developing structural problems that threatened to negate all those production miracles. If Liberty ships couldn't be trusted to survive North Atlantic crossings, if they might break apart without warning, then what was the point of building them at such frantic pace? Military planners faced an impossible dilemma. The invasion of Europe, already being planned for spring or summer of 1944, would require thousands of ships to transport troops and supplies across the English Channel and sustain operations on the continent. Liberty ships were supposed to form the backbone of that logistics network, but could they be used if they might fracture catastrophically? The U.S. Coast Guard was recommending that Liberty ships be withdrawn from troop-carrying duties, yet military commitments required their continued use. There simply weren't enough other vessels available. The pressure to find answers intensified. The Maritime Commission, the Navy Department, the Coast Guard, and the Warshipping Administration all launched investigations. Teams of inspectors, naval architects, and metallurgists descended on shipyards and examined failed vessels. They studied construction records, interviewed workers, analyzed steel samples, and searched desperately for the cause of these mysterious failures. The Welding remained the primary suspect. Critics pointed to the inexperienced workforce, the abbreviated training, the pressure to meet production quotas. Perhaps Kaiser's revolutionary methods were too revolutionary. Perhaps you couldn't train housewives and farmers to be welders in a few weeks and expect them to produce reliable work. Perhaps the traditional shipbuilders had been right all along. Ships required skilled craftsmen and couldn't be mass-produced, like automobiles. Kaiser defended his workers vigorously. He argued that weld quality inspections showed most welds were sound. The defect rate in Kaiser's yards was actually lower than in many traditional shipyards, while the U.S. government found that more than 20% of ships made by other builders had serious defects. The defect rate for Kaiser ships was less than 10%. The problem couldn't simply be poor workmanship, but the criticism stung, particularly for the women and minority workers who had proven themselves capable of performing complex industrial work under enormous pressure. Rosie the Riveter, though most of them were actually welders, had become a symbol of American homefront mobilization. Now, some were suggesting that these workers were literally killing American sailors through incompetent welding. The accusation was unfair and, as it would turn out, completely wrong. But in late 1943 and early 1944, with ships cracking and breaking, with lives being lost, the search for scapegoats was inevitable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The breakthrough came from an unexpected source, a British woman scientist who had spent decades studying the crystalline structure of metals. Constance Fligg Tipper was 49 years old in 1943, a lecturer in the Department of Engineering at Cambridge University. She had been appointed as one of the first women lecturers at Cambridge in 1939, at a time when many male lecturers had left for wartime work. Her specialty was metallurgy and crystallography, the study of how metals behave at the atomic level and how their internal structure affects their properties. Tipper had been born Constance Fligg Elam in 1894 in New Barnet, Hertfordshire, the daughter of a surgeon. She had studied engineering at Plains-Shipped Newnham College, Cambridge, in 1912, among the first women to take the natural sciences tripos. In 1915, she joined the metallurgical department of the National Physical Laboratory, then moved in 1916 to the Royal School of Mines, where she was appointed research assistant and later elected to a research fellowship. In 1928, she married George Tipper, a geologist, and settled in Cambridge, where she would continue her research for more than 30 years. Her work focused on understanding how metals deform and fail. She had published papers on slip bands in crystals, on plastic deformation, on the relationship between a metal's microscopic structure and its macroscopic properties. This was esoteric, academic research, far removed from the practical concerns of wartime shipbuilding. Yet, it would prove essential to solving the Liberty ship mystery. The British Admiralty Ship Welding Committee engaged Tipper to lead the metallurgical investigation into why Liberty ships were cracking. The British had their own stake in understanding the problem. They had ordered the original 60 ships that became the prototype for the Liberty design. British shipyards were also building ocean-class vessels using welded construction, and British convoys were suffering losses not just from U-boats but from structural failures of merchant vessels. Tipper approached the problem with scientific rigor. She obtained steel samples from Liberty ships that had failed, including plates where fractures had originated. She subjected these samples to mechanical testing, measuring their properties under various conditions, and she made a discovery that would transform the understanding of structural failure. The steel used in Liberty ships was not defective in any conventional sense. It met all the specifications that had been established for shipplate steel. In laboratory tests at room temperature, the steel showed good ductility, ability to deform plastically before fracturing. It could bend, stretch, and absorb considerable energy before breaking. This was exactly what steel was supposed to do. But Tipper discovered that the steel's behavior changed dramatically at low temperatures. She used what is now known as the Charpy impact test, dropping a swinging pendulum onto compact samples containing a standard notch, measuring the energy required to fracture the specimen. When she tested Liberty ship steel at room temperature, the samples absorbed significant energy and showed ductile fracture characteristics. When she tested the same steel at temperatures around 32 degrees Fahrenheit, typical of winter conditions in the North Atlantic, the energy absorption dropped precipitously and the fracture mode changed to brittle failure. The phenomenon was called the ductile to brittle transition. Above a certain temperature, the steel behaved in a ductile manner, deforming plastically and absorbing energy, before fracturing. Below that critical temperature, the steel became brittle, fracturing suddenly with minimal energy absorption and no visible plastic deformation. The transition temperature for Liberty ship steel averaged around 75 degrees Fahrenheit, though it varied from sample to sample. Some plates had transition temperatures as high as 150 degrees Fahrenheit. This meant that approximately 90% of the steel samples Tipper tested would exhibit brittle behavior at temperatures below 45 degrees Fahrenheit. Ships operating in the North Atlantic during winter were routinely exposed to air temperatures well below freezing and water temperatures in the mid-30s. Under these conditions, the Liberty ship steel wasn't just cold, it was operating well below its ductile to brittle transition temperature. The steel had become fundamentally different material than it was in the warm shipyard where it had been fabricated and tested. It had become glass-like in its brittleness, capable of fracturing catastrophically with minimal warning. Tipper's discovery explained the puzzling pattern of failures. Ships cracked more frequently in winter because that's when temperatures dropped below the transition point. Ships in the North Atlantic failed more often than ships in warmer waters for the same reason. The Schenectady had split in half at the dock on a cold January morning when the steel's temperature had dropped below its transition point, making the hull brittle enough that normal thermal stresses from uneven cooling were sufficient to initiate a catastrophic fracture. But Tipper's research revealed an even more critical aspect of the problem: the role of welding in propagating cracks once they started. In a riveted ship, steel plates overlapped and were held together by mechanical fasteners. If a crack developed in one plate and propagated to the edge, it would stop at the rivet line. The crack couldn't easily jump across the gap between plates. The riveted joint acted as a natural crack arrestor, limiting the damage to a single plate or a small section of the hull. In a welded ship, there were no such natural crack arrestors. The entire hull was a continuous structure of steel plates fused together by welding. A crack that initiated anywhere could propagate through the welded joints without stopping. And in cold, brittle steel, once a crack started, it could travel at nearly the speed of sound through the material. The continuous welded structure that made Liberty ships so quick to build also made them vulnerable to catastrophic crack propagation in a way that riveted ships were not. Tipper's findings were definitive. The problem wasn't the welding process itself. The problem wasn't incompetent workers or rushed production. The problem was the fundamental behavior of the steel at low temperatures, combined with the continuous welded structure that allowed cracks to propagate unimpeded. Even if every single weld had been perfect, Liberty ships would still have been vulnerable to brittle fracture in cold conditions. The discovery absolved Kaiser's workers of blame and vindicated the welding process as a construction method. But it also presented a daunting challenge. How do you fix a problem that's built into the material itself and the fundamental design of 2,000 ships already at sea, with hundreds more under construction? The solution required multiple approaches, implemented simultaneously. The most immediate fix was operational. Route Liberty ships through warmer waters whenever possible and avoid sending them into the coldest regions of the North Atlantic during winter months. This was a logistical nightmare for convoy planners, who had to balance shipping routes against U-boat threat patterns, weather conditions, and strategic priorities. But it was implemented wherever feasible. Ships that had to operate in cold waters were monitored more carefully for crack development. The second approach was retrofitting existing ships with crack arrestors. Engineers designed riveted steel straps that could be installed along the length of the hull at strategic locations. These straps, which interrupted the continuous welded structure, would act like the natural crack arrestors in riveted ships. If a crack developed and began to propagate, it would slow down or stop when it reached a riveted strap. The Maritime Commission mandated that all Liberty ships be fitted with at least 4 longitudinal crack arrestor straps. Two tankers, which had suffered some of the worst failures, were required to have additional reinforcement. Installing these retrofits required pulling ships out of service, a costly delay when every vessel was desperately needed. But the alternative, losing ships and crews to catastrophic failures, was worse. Shipyards worked around the clock to modify vessels. Some modifications were performed during regular maintenance periods. Others required emergency dry docking. The work continued throughout 1944 and into 1945. The third approach addressed the root cause: improve the steel itself. Metallurgists worked with steel mills to develop improved grades of ship plate with lower ductile to brittle transition temperatures. The goal was steel that would remain ductile even at the coldest temperatures ships might encounter. This required adjusting the steel's composition, controlling impurities more carefully, and modifying manufacturing processes. Sulfur, for example, made steel brittle and harder to weld, so sulfur content was reduced. Manganese was increased to counteract sulfur's effects. New steel specifications were developed and implemented for ships built after late 1944. These improved steels had transition temperatures well below freezing, making brittle fracture much less likely even in the harshest winter conditions. But developing and implementing new steel grades took time. Ships already built or under construction in 1943 and early 1944 were still vulnerable. The fourth approach focused on design modifications to reduce stress concentrations that could initiate cracks. Square corners on cargo hatches were identified as particularly problematic. The sharp corners created stress concentrations, locations where stress was much higher than in surrounding areas. When these stress concentrations coincided with welded seams, as they often did, the combination could initiate a crack in cold, brittle steel. Engineers redesigned the hatch corners, adding rounded transitions instead of sharp 90-degree angles. This distributed stress more evenly and reduced the likelihood of crack initiation. They also strengthened areas around hatches and other discontinuities in the hull structure. These design improvements were incorporated into Victory ships, the improved successor to the Liberty design that began production in 1944. Victory ships incorporated everything learned from the Liberty ship failures. They used improved steel with better low-temperature properties. They had rounded corners on hatches and other openings. They were designed to be less stiff, with frame spacing increased from 30 inches to 36 inches, making the hull more flexible and better able to accommodate stress without concentrating it at vulnerable points. The wider frame spacing also made the ships lighter and faster, improving their performance while simultaneously reducing their vulnerability to brittle fracture. The improvements worked. While Liberty ships continued to experience some cracking throughout the war, the rate of catastrophic failures dropped significantly after the modifications were implemented. The combination of better steel, crack arresters, design improvements, and operational procedures reduced Class I failures to manageable levels. Liberty ships continued to serve throughout the remainder of the war, carrying millions of tons of cargo and ultimately proving indispensable to Allied victory. But the cost had been real. Approximately 12 Liberty ships broke completely in half. 3 of those sank with loss of life. Nearly 1,500 instances of significant brittle fractures were recorded. Countless more minor cracks required repair. The economic cost of modifications, repairs, and lost service time ran into the tens of millions of dollars. The human cost of those who died when ships broke apart was incalculable. Constance Tipper's contribution to solving the crisis was recognized by the engineering community, though her name never became widely known outside specialist circles. She continued her research at Cambridge until her retirement in 1960, then worked as a consultant on submarine construction in northwest England. She became the first person to use a scanning electron microscope to examine metallic fracture faces, using a device. Built by Charles Oatley's team at Cambridge, only the second scanning electron microscope ever built. In 1955, she was awarded the Thomas Lowe Gray Prize, jointly with Professor J.F. Baker for their paper on notch tensile testing. The test she developed, now known as the Tipper test, became the standard method for determining the ductile to brittle transition temperature of steel. Modern steel specifications require impact testing at specified temperatures to ensure materials will perform safely in service conditions. Tipper lived to the remarkable age of 101, passing away in 1995. Her 100th birthday in 1994 was celebrated at Newnham College with the planting of the Tipper tree, a sweet chestnut that still stands today. The Liberty ship failures became a foundational case study in the emerging field of fracture mechanics. Before World War II, engineers understood that materials could fail through yielding excessive plastic deformation or through ductile rupture after extensive deformation. But brittle fracture, where a tough material suddenly fails with no warning and minimal deformation, was poorly understood. The Liberty ships forced the engineering community to develop a systematic understanding of how cracks initiate and propagate, how material properties change with temperature, and how design details can concentrate stress in dangerous ways. The lessons learned from Liberty ship failures influenced ship design for decades. Modern ships avoid sharp corners and discontinuities wherever possible. Steel specifications require verification of low-temperature toughness through impact testing. Naval architects understand that welded structures require careful attention to crack propagation paths and may need crack arresters in critical areas. The continuous welded construction that caused such problems in Liberty ships is now routine, but only because engineers learned to account for the 10 factors that made such construction vulnerable. The irony was profound. Henry Kaiser's revolutionary methods had succeeded brilliantly. His prefabrication techniques, assembly line production, and use of welding instead of riveting had enabled America to build ships faster than any nation in history. The Liberty Ship program produced 2,710 vessels in less than 4 years, an achievement that symbolized American industrial might and helped win World War II. Welding made that achievement possible. Yet welding had also created a vulnerability that killed American sailors and nearly undermined the entire program. The same continuous welded structure that enabled rapid construction also enabled catastrophic crack propagation. The innovation that won the logistics war in the Atlantic also made ships that could break in half without warning. The problem wasn't that Kaiser was wrong to use welding. Given the constraints of wartime production, the need for speed, the shortage of skilled labor, the requirement to build thousands of ships, welding was the only viable approach. Riveting simply couldn't have produced vessels at the required pace. The problem was that neither Kaiser nor anyone else fully understood the material science implications of creating large welded structures from steel that became brittle at low temperatures. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.